Hello guys, I'm back. In this video, I will show you the main aspects of material streams on Aspen Plus, and I will teach you how you need to know to match the information of volume flow from your process and from your production to the process simulation results. My name is Jeferson Costa, and my mission is to oversimplify chemical process engineering and plant design to you. To do that, I will cover the following subjects: the standards inputs on Aspen Hysys, composition bases, what are the kinds of flow available on Aspen Hysys, flow measurement, and finally, which information to be used in your process simulation. First steps to start a process simulation on Aspen Hysys includes adding a list of components and also choosing a fluid property package to your process simulation. If you are not familiar or if you don't know how to do that yet, I recommend you to go to my video Hysys tutorial for beginners, because there I give you the step-by-step. Here I will start with the material stream already added to the process simulation environment. To let our life easier, I will use as example a feed water stream for this process simulation. So every time that I need to add a material stream to my process simulation on Aspen Hysys, I will use the blue arrow that represents material streams to my process. If I need to add some kind of energy to my process simulation, I will use the red arrow. In this video, we will not talk about energy stream, we will only focus on material streams. Once you add that to your process simulation, it will be identified as a light blue color. It means that the stream is available for filling information related to that. When I click 2 times on that, a submenu will open and you can see that there are some information that is missing, and every field that you have here on blue means that you are able to add the information. Attention that Aspen Hysys helps you to fill the process simulation. So in this case, the yellow bar gives you some kind of advices. So the first thing that the process simulation recommends you to do is add the information for composition. But before doing that, let's talk about some standards inputs needed to define a material stream on Aspen Hysys. Most often, once the composition of your material stream is defined, what you will add as conditions to your process simulation is information related to phase fraction, temperature or pressure, and the fluid flow of the process. With that, Aspen Hysys will perform calculation and fill the information for the other parameters. And the identification of your material stream will change from light blue to dark blue. In this case, to proceed with the specification of the material streams, let's go to the option composition. Although I have only water as my components for this example, I can change the composition basis of this process simulation. I have 2 ways to do that. One of the ways is clicking on bases, and it will open to me a submenu where per standard, the first time that you use the Aspen Hysys, it will be checked as mole fraction. So from 0 to 1, you can specify how much or the amount of components that you have. In this case, as I have only water, it's mandatory that I have 100% mole fraction. But I can specify also as mass fraction, liquid volume fraction, mole flow, mass flow, and also liquid volume flow. And here is where the misunderstanding happens, because the Aspen Hysys has different kinds or different types of liquid volume flow. And we'll talk about that a little bit in this video. Another way to change the component basis of your process simulation is to adding some value to the tab where you need to define the composition of your stream. For instance, if I type 1 and click on enter, a submenu will open, and you have also the option to change the composition basis of your process simulation. As I told you, per standard, the mole fraction is the option checked by the Aspen Hysys. And here, what is important to understand that every time that you choose fractions as composition basis, the summing up of all the composition must be 1. If it is under, below 1, or above 1, the Aspen Hysys will do arrangements to the totalization be 1 again. In this case, I will let the composition basis of my process simulation as mole fraction once I have 100% water in my material stream, and after that I click on OK, and the warning from unknown composition changes from for unknown temperature. So now it's time to fill the conditions of my process simulation. To do that, it's time to go to conditions, and just to have a reference to starting filling the information for my example, let's consider that temperature is 85 Celsius degree, and now that I have the temperature, if I define the pressure, the phase fraction will be defined. Or if I define the phase fraction, the pressure will be defined. So let's verify that. If I type 0 to phase fraction, it means that I have a saturated liquid, and the Aspen Hysys will calculate the pressure referred to this condition. On the other hand, if I type 1, I have saturated vapor, and the saturated vapor and saturated liquid is in equilibrium, so the pressure is the same. But if I change, or if I delete the phase fraction and define my pressure, for instance, as 5.5 bar G, now I have the calculation of the phase fraction. All the values that appears in the Aspen Hysys as black means that is something calculated by the Aspen Hysys. So in this case, I am not able to add information related to molar enthalpy nor molar entropy. If I delete pressure, molar enthalpy, molar entropy is now available as an input to my process simulation. As I told you, most often, usually you don't use this kind of information. So, many cases, what we define is pressure, temperature, and phase fraction. And now it's time to finish the specification of my material stream. It's time to define the flow rate. The flow rate can be defined as molar flow, mass flow, standard ideal liquid volume flow, or liquid volume flow. If I add information for heat flow, I will also define my material stream. But most often that what we use is molar or mass. Here you will observe that my molar flow is the unit of measurement is normal cubic meter per hour gas, but that is not the standard condition for the Aspen Hysys. If I click in unit set, I will return the molar flow as by the standard of the Aspen Hysys. That is kilomole per hour if I use the SI or similar units of measurement. So the kilomole per hour, it's not a usually used unit of measurement in the chemical process engineering and plant design projects, because we don't sell products as kilomole per hour, or we don't measure products as kilomole per hour. Most often you find molar flow as kilomole per hour or mole per hour when you have test books showing with you or sharing with you examples on how to perform chemical process engineering calculations, or eventually if you work with lab or chemical reactions, eventually you will use the information as kilogram mole per hour as input to your process simulation. In real life, most often we use the mass flow or its variation as ton, or the molar flow, but not as kilogram mole per hour, but as normal cubic meter per hour or standard cubic meter per hour when we are talking about gases. So if I go to unit set, I can change the unit of measurement of my molar flow, and here I have a list of options for my process simulation. So I have kilogram mole per time, I have cubic meter per time, I have normal cubic meter per time, and we'll see the differences between the cubic meter per time and also normal cubic meter per time. For a while, I will let the kilogram mole per hour as the unit of measurement for this process simulation. So I will define here my stream as 1000 kilograms per hour of flow, and once I click on enter, you can see that my yellow bar becomes green bar, and it means that my material stream is fully specified, and now I have the dark blue color. If you deal with mass flow in your process simulation or molar flow as kilomole per hour, probably you will not find any kind of issues to understand the results of your process simulation in terms of mass flow and molar flow. However, if people are dealing with liquid volume flow as input, the understanding of this parameter can be challenging, because the Aspen Hysys has three kinds of liquid volume flow in the process simulation. One of them is the standard ideal liquid volume flow, and you can see here that the information calculated is 1.002. The Aspen Hysys has also liquid volume flow at standard conditions, cubic meter per hour, also the same unit of measurement, but the calculation performed 1.001. And we have also, if you go to properties, you will see that you have the actual volume flow, that in this case is the actual liquid volume flow that is calculated as 1.033, and no one of them are the same, although all of them are talking about volume flow. To understand what is happening, let's return to the composition basis. Every time that you define a stream as liquid volume flow, the Aspen Hysys will perform a calculation based on the mass density of the components. But the mass density of the components is a function of pressure and temperature, so the Aspen Hysys needs to have a reference to perform this calculation. So in the composition basis, the definition of pressure and temperature for the calculation is 60 Fahrenheit and 1 atm if you are using the field units, or 60 Celsius degree and 1 atm if you are using the national system of units. With that, the Aspen Hysys will get the information of the liquid volume flow and will perform the calculation for the mass flow of the component. As Aspen Hysys has three different kinds of liquid volume flow, you must understand how the software performs the calculations of each mass density. So in this case, when we are talking about standard ideal liquid mass density, the Aspen Hysys will do calculations based on 60 Fahrenheit, but depends on if the component is a liquid at 60 Fahrenheit and 1 atm, the Aspen Hysys will use a data if the component can be liquefied at 60 Fahrenheit, but in a pressure above 1 atm, they will use the saturation pressure, so it will be another reference for mass density. And if the conditions do not apply to case 1 and case 3, the Aspen Hysys will use information from GPA. And that can lead to very different results when you are performing your process simulation. When we are talking about liquid mass density at standard conditions, in this case, the Aspen Hysys will use as reference the volumetric flow at 60 Fahrenheit and 1 atm. And when we are evaluating the results for the actual liquid volume flow, the Aspen Hysys will perform the actual liquid density based on the process conditions or operating conditions of pressure and temperature. So let's go to the Aspen Hysys and verify how it is in the practice. A way to verify the changes in the three kinds of liquid volume flow on Aspen Hysys at the same time is adding a table to my process simulation. To do that, I just need to highlight my material stream, click with the right button of my mouse, and I will choose Show Table. With that, I have a table with some standard information like temperature, pressure, molar flow. If I click 2 times, I can add variables, and in this case, I will add the variables related to liquids. I want the actual liquid volume flow or actual liquid flow. I want the liquid flow at standard conditions. And finally, I want the standard ideal liquid volume flow. So with that, I have the 3 information in my process simulation. I can verify that them in just one place. Verify that my actual liquid volume flow is based on cubic meter per second. So I will change that to let our life easier. Let's return to unit set. And at the top, I have the actual gas flow and actual volume flow and actual liquid flow. So I will change that to cubic meter per hour. Click on OK. Now all of them are at the same basis. So what I will do to evaluate what's happening? We have seen that the liquid volume flow at standard condition are based on 60 Fahrenheit and 1 atm. When I do that, my actual volume flow matches with liquid volume flow at standard conditions. In this case, the Aspen Hysys get the information of the mass density as a calculation of the process based on the pressure and temperature at standard condition. But when we are talking about standard ideal liquid volume flow, the information of mass density comes from the database of the Aspen Hysys. So eventually, because the roundings of the numbers will not have the same value, we can verify the reference for the mass density, returning to the feed stream, going to properties, and here I have the mass density used to perform the calculation of the liquid volume flow at standard condition, 998.9. If I want to verify what is the standard ideal liquid mass density, I can return to my properties, double click on my components, and here I will verify what is the value considered for the calculations. Ideal liquid density as 998.0. So you can see that there is slight differences between ideal liquid density and the mass density at standard conditions. And that justifies the differences in the results. Up to this point, we talked about liquids, but you must be aware also when we are dealing with gases, because the Aspen Hysys we use molar volume as an ideal mixture at the standard conditions to do the calculations of volume flow of gases. Based on that, the references of temperature and pressure will be the 60 Fahrenheit at 1 atm, and the Aspen Hysys we use as a value of reference the molar volume, that is 375.46 cubic feet per pound mole, or we have to 23.644 cubic meters per kilogram mole. This is for ideal gases, and this is the references for the volume flow of gases in the Aspen Hysys. If you want to have the conditions as 0 Celsius degree, that is the normal cubic meter per hour, you need to choose the correct unit of measurement. So I will show you now how is the differences that you have in the results when you are dealing with the gas information and when you choose normal cubic meter per hour and just cubic meter per hour, both of them for gases. To be able to verify what is the volume flow conditions for gas in my standard conditions, in my conditions in the worksheet, I must change the molar flow from kilograms mole per hour in my unit set. To that, I just need to click and verify the molar flow. And now I will change the information from kilograms per hour to cubic meter per hour of gas. Verify that although my material stream is a liquid because I have phase fraction as 0, if I change the unit of measurement to cubic meter per hour gas, I will have a molar flow in terms of cubic meter per hour of gas as 1,320 cubic meters per hour. This is not the kilograms mole per hour anymore. Now what I have here is the conversion of 1,000 kilograms per hour of water to a gas flow. If I change the cubic meter hour to normal cubic meter hour of gas, my value will change from 1,312 to 1,244 normal cubic meters per hour of gas. So in this case, Aspen Hysys is considering that this amount of water, although it is in liquid phase, now my information is in gas phase. Verify that for normal conditions, 0 Celsius degree and 1 atm, water will not be a gas. But in any case, the Aspen Hysys is using the convention of 22.455 cubic meters per kilogram mole of the component to do the calculation. Let's close this one, and we can add more information related to flow here in the tab. So now let's add the actual volume flow and also the actual gas flow. That done, we have here 0 for actual gas flow because at these conditions the stream is as liquid, but if I change the conditions, I can vaporize my water. So in this case, I will consider atm, and let's with 150 Celsius degree. So now I don't have actual liquid flow, it's 0. My liquid volume flow at standard condition is the same because it's based on 60 Fahrenheit and 1 atm. The standard ideal liquid volume flow is the same because it is considering the standard ideal mass density at 60 Fahrenheit and 1 atm. My actual volume flow is 1,911 cubic meters per hour. It doesn't identify if it is liquid or gas, and now I have my actual gas flow as 1,911 actual cubic meter per hour, and verify that this number will not match with this number because they are in different conditions. Based on what we have seen, what happens in real life. In real life, we have different kinds or different types of flow measurement. For instance, we have differential pressure flow meters, velocity flow meters, mass flow meters, positive displacement flow meters, open channel meters, and all of them will give it to you, will read in your process the volume flow based on the operating conditions, based on the pressure, temperature, and the mass flow that is going in your process. The flow meters will perform the calculations, and for the same mass that you have in your process, if you change the pressure and temperature, the information of flow will be different. So when we are dealing with process operation, most often depending on how critical is the information of flow to the process, we have the compensation of the values. We need to convert the actual volume flow that we have in the process into a standard volume flow that we know the basis of pressure and temperature to always have the same references for the process. That is especially important when we are talking about gases because they are compressible fluids, and a variation pressure and temperature can vary a lot the mass density of the fluid, and that can give you totally different numbers of measurement to the same mass flow that you have in your process. In liquids, it's not so common to have this kind of compensation, but eventually you can find it if you are talking about custard transfer and we are talking about billing, but I have never seen this kind of situation. So what happens when you are trying to get the information from the field and transport to your process simulation? You need to know what are the bases of your measurement in your process. To use your actual volume flow as an input to your process simulation, you have two ways to do that. One of them is with your actual volume flow and with the mass density of your fluid, you do the calculations of the mass flow and add that to your process simulation. So instead of informing the actual volume flow, in fact, you will inform the mass flow to your process simulation, and that will correspond to your actual volume flow. But you can use also the function spreadsheet, and you can set an equation in order that you input the actual volume flow. The Aspen Hysys do the calculation for the mass flow, and the Aspen Hysys for the information for your process simulation. And with that, instead of changing the mass flow, change the actual volume flow. This is not the object of this class. I may return with this subject in another moment. If you let me know in the comments if you would like to have this kind of video or not. To finish this video, let me share with you a case study that I received a request of help on my LinkedIn, and this is about the subject that we are just talking about. So the Tarek verified that the actual volume flow was bigger than the total volume flow shown in composition. So he would like to evaluate the production based on barrels day, and he was not understanding why in the liquid volume flow tab, the summing up was below them or was different than the information available at the actual volume flow as barrel per day. And as you have seen in this live session, the differences are because they have different phases. The actual volume flow is based on the operating conditions, pressure and temperature, and the liquid volume flow is based on 60 Fahrenheit and 1 atm conditions. So if the process is not running at 60 Fahrenheit and 1 atm conditions, the calculation of the mass density will not be the same, the results of the mass density will not be the same, and these values will not be the same because of that. So when you understand what you are doing in the Aspen Hysys and you know the fundamentals of chemical process engineering, it is much easier to evaluate the results that you have on your process simulation. So guys, that's it. I hope you like it, and I'll see you soon in the next video.